Important quantum algorithm can really be a property of nature. September 17, 2019. Evidence that quantum research is a common feature of electron behavior may explain the genetic code, one of the biggest puzzles in biology. Important quantum algorithm can really be a property of nature. MS Tech. Original image, Wikimedia Commons. In 1996, a quantum physicist from Bell Labs in the state of New Jersey published a new recipe to search a database of n entries. Computer scientists have long known that this process takes about n steps because, at worst, the last item on the list may be of interest to you. However, this physicist, Love Grover, showed how the strange rules of quantum mechanics allowed the research to be performed in several steps equal to the square root of n. That was a breakthrough. Searching databases is a fundamental computer science task, used for everything from finding phone numbers to breaking cryptographic codes. Therefore, any acceleration is a significant advance. Quantum mechanics provided an added touch. At the time, Grover's recipe was just the second quantum algorithm that had been proven faster than its classic equivalent. The first was Peter Scher's algorithm for number factorization, which he discovered in 1994. Grover's work was an important factor in paving the way for the quantum computing revolution that is still underway today. But despite the interest, the implementation of Grover's algorithm took time due to the significant technical challenges involved. The first quantum computer capable of implementing it appeared in 1998, but the first scalable version did not appear until 2017, yet it worked with only 3 qubits. Therefore, new ways to implement the algorithm are desperately needed. Today, Streetheim Gillett and colleagues at the University of Toulon, France, say this may be easier than expected. They say they have evidence that Grover's search algorithm is a natural phenomena. They said, "We provide the first evidence that, under certain conditions, electrons can behave naturally like a Grover research, looking for defects in a material." This has obvious implications for quantum computing, but its actual import can be much deeper. For some time, theorists debated whether quantum research could explain one of the greatest mysteries about the origin of life. The idea that Grover's research takes place in the wild could finally solve the puzzle. First, some background. Because it is so fundamental, Grover's search algorithm can be redesigned in a number of ways. One is like a quantum walk across a surface, the way a quantum particle would move randomly from one point to another. Clearly, this process is a kind of two-dimensional space search. But because a quantum particle can explore many paths at once, it is much faster than classical research. The nature of the surface has an important influence on research. For example, a surface type consists of a square grid in which the quantum particle has 4 possible motions at each vertex. But there are many other possible grids. A triangular one, for example, where the quantum particle has 3 options at each vertex. Gillett and colleagues say the triangular grid is of particular interest because of its similarity to various natural crystal-like materials. The team focused on simulating the way a Grover research works for electrons by exploring triangular and square grids, but also included other physically realistic effects, such as whole grid defects and quantum properties, such as interference effects. The results are revealing. The question they ask is how quickly an electron can find the hole in a grid. And the breakthrough of the team is to show that these simulations reproduce the behavior of real electrons in real materials. In other words, this is evidence that free electrons naturally implement Grover's search algorithm as they move across the surface of certain crystals. This has immediate implications for quantum computing. The team reported, "This work may be the path to a serious technological leap, whereby the experimentalist would ignore the need for a scalable, error-correcting quantum computer, and take the shortcut to look for natural occurrences of Grover research." The work also has implications for our thinking about the genetic code and the origin of life. Every living thing on Earth uses the same code, in which DNA stores information using 4 nucleotide bases. Nucleotide sequences encode information for protein construction from a 20 amino acid alphabet. But why these numbers, 4 and 20, and not others? In 2000, just a few years after Grover published his work, Apurva Patel of the Bangalore Indian Institute of Science showed how Grover's algorithm could explain these numbers. Patel's idea is related to the way DNA is assembled within cells. In this situation, the molecular machinery within a cell must search through the molecular soup of nucleotide bases to find the correct one. If there are 4 options, a classic search performs 4 steps on average. Therefore, the machinery would need to try 4 different bases during each assembly step. But a quantum search using the Grover algorithm is much faster. Potel showed that when there are 4 options, a quantum search can distinguish between 4 alternatives in one step. In fact, 4 is the ideal number. This thinking also explains why there are 20 amino acids in DNA. Each set of 3 nucleotides defines a single amino acid. Therefore, the sequence of triplets in DNA defines the amino acid sequence in a protein. But during protein assembly, each amino acid must be chosen from a soup of 20 different options. Grover's algorithm explains these numbers. A 3-step quantum search can find an object in a database containing up to 20 input types. Again, 20 is the ideal number. In other words, if the search process involved in assembling DNA and proteins is as efficient as possible, the number of bases must be 4 and the number of amino acids must be 20, just as it is found. The only caveat is that research must be quantum in nature. When Potel published his idea, quantum physicists immediately criticized it. At the time, they were bogged down in their own attempts to control quantum processes, which they could only do by isolating quantum particles in extreme environments, such as temperatures near absolute zero. The obvious problem, they said, was that living things operated in a hot and disorderly environment in which quantum states would be immediately destroyed. Biologists were equally dismissive, saying that quantum processes could not be working within living beings. Since then, a growing body of evidence has emerged that quantum processes play an important role in various biological mechanisms. Photosynthesis, for example, is now considered an essentially quantum process. The work of Gillette and Company launches a new perspective on all this. This suggests that the Grover algorithm is not only possible on certain materials. It seems to be a property of nature. And if this is true, then objections to Patel's ideas begin to crumble. It may be that life is just an example of Grover's quantum research at work and that this algorithm is a fundamental property of nature. That is a great idea, if there ever was one.